Okay, I see people on screen. A challenging environment here in Egypt, as well as challenging environment in Antarctica, as well as challenging environment in Ukraine. So many challenges cause so big problem here with connection. But after all, we, I hope, solve everything, and we are ready to start. So this event supposed to be more positive than our previous one, because we want to speak on this day of science and youth about science in Antarctica on our Ukrainian Antarctic station, academic Vernadsky, and we'll be speaking on youth there as well, of course, because it's really very our young, it's a possibility for young people to be there, to realize themselves in this interesting environment as well. And this station actually maybe not so young. Of course, it's not so young because the station has the longest actually data for climate research in Antarctic Peninsula region. But first of all, I would like to present myself and to say a few words just to explain why I am here and why I present this. Today is Youth Day, so I wear this special T-shirt with Antarctic emblem, but actually I represent Ukraine at Intergovernmental Panel on Climate Change, and this is me just a year ago in Glasgow. With the report, I authored this report, this Working Group 1 report on physical climate, on physical science basis of climate change, and this is summary for policymakers where I contributed. And here is Ed Hawkins, who actually proposed to make this fashion thing like stripes. I have this one here. So this fashion, just to remind ourselves how temperature changed from this industrial era up to this red one. So please, next. Yeah, so this is exactly a year ago. I was involved in this event in Central Asia, where I spoke on this regional focus of IPCC. And today we move this focus to Antarctica. So I worked for Central Asia, for East Europe, and for Antarctica as well. So and today I represent our National Antarctic Scientific Center here. Please, next. And with this, yeah, just to show you on this web page of IPCC report, you can find myself as well. So here am I, just over the clouds. Nobody knows, but you will know. Okay, so please, next. Next slide, please. Yeah, just to explain. So I found myself as witness of climate change because, yeah, 25 years ago, I was at this time in Antarctica, and I was witness of climate change from that time, and it was first time when I actually was thinking about climate change, because this is a picture actually from my time when I was there, and I'm pretty sure that scientists who were at Antarctic station, they will not recognize it, or it has a different shape because of climate change. And actually this year, it's just destroyed. So you don't find this environment as well in Antarctica anymore. So please, next. Yeah. And today, actually, we have very extensive program with distinguished speakers from all over the globe who devoted their life. I would be clear to this remote place of the Earth, And I will not speak on themselves, but I will just stop here, and I guess we will see this video. So please just put the video on. Yeah, we will stop now. And actually, Antarctica is indeed a very important place for all us on the Earth. And I really surprised to see in this environment so big vegetation. For me, it was not the case when I was there. And with this, we will continue to listen how actually this climate change, which is the most rapid actually in Antarctica, in this our site of Ukrainian Antarctic Station. So I will give the floor to Maria Pavlovska, who will speak on this impact of climate change on flora and fauna. So floor is yours.
Hello, hi everybody. Can I demonstrate my screen, Svetlana, or will somebody demonstrate it? Okay, I think I have the possibility to demonstrate anyway. Okay.
So Maria, if you can, please share your screen.
Yeah, I will try to share my screen. It will be easier if I will do it on my own. So just wait a sec. Okay. Yeah,
as far
I think
as I understand, you are in Kyiv now.
Can you see my screen?
Yeah, it's, just put it in a full screen, I guess.
Okay, good.
Yeah, great.
Yes, hello everybody once more. I'm really happy that we have the possibility to participate in this forum and to present now and take into account the technical issues and blackouts in Kyiv. I'm happy that I have the technical possibility of doing this. So my presentation will be about the biological consequences of the climate change in Antarctica, about the impact of climate change on flora and fauna in Antarctic Peninsula region. So why are we talking about Antarctic Peninsula? Why this part of the Antarctica matters? First of all, Antarctica does not warm up in the same manner on the peninsula and on the continent. Many continental regions have not exhibited such significant change in temperature and such a shrinkage in ice over the past century. At the same time, during the period of 1950-2000, annual mean temperatures in Antarctic Peninsula rose by 3 degrees or more in some parts. For instance, sea temperatures in Bellingshausen Sea to the west of the Antarctic Peninsula, it's here, increased by 1 degree. And the ice-free area is predicted to increase by 25% in the next century across the entire continent, but it will increase much more in Antarctic Peninsula. The predicted increase in ice-free area in the peninsula is 300%, which is really, really high. This picture illustrates the changes in the temperature and in ice cover in Antarctica. It's for the data that started in the 20th century and then up to the 2009. So this was the climate change, the warming that had been already observed in Antarctica. You can see that Antarctic Peninsula is warming up much more than the rest of the Antarctica. First, I will talk about terrestrial ecosystems and the impact of climate change on them, and then we'll move to marine ecosystems. So terrestrial ecosystems of Antarctica are really peculiar because they are isolated from lower latitude land by geographical distance, by the ocean, by atmospheric circulation. And the terrestrial ecosystems are really vulnerable, and they're really small. They're tiny, actually, because this ice-free ground is just a tiny proportion of the continental area. So if you compare this terrestrial ecosystems in the peninsula and maritime Antarctica, they are really, really small. They occupy just an area of 0.5% of the whole Antarctica. And it consists of many isolated islands in the ocean. The diversity in terrestrial ecosystems is low, but it is really peculiar. It's unique. It's endemic. And basically, all these islands that are separated by the ocean represent very unique diversity patterns. And the diversity is represented by microarthropods, microinvertebrates, mostly lower plants, mosses, lichens, and the microbes. This peculiar biodiversity is really stress tolerant because they face the low temperature, desiccation, light UV influence, also low nutrients, small amount of soil, but still this diversity is adapted to these peculiar conditions. And it is really understudied. So basically the consequences of climate change on the terrestrial diversity in Antarctica are still studied by the scientists. As with any factor, we have the positive and negative influence. The positive influence that is predicted by scientists is that more snow and ice melt will release more liquid water, and liquid water is really needed by vegetation to expand. So we predict that we'll have more areas that can be colonized by plants in Antarctica. And this will lead to increased productivity, to the population growth, and to expanded local distributions. But at the same time, the negative consequences are the exhaustion of the resource supply, because if we will have more species and more populations occupying some land, the competition for the resources will be also higher, and we don't know how our diversity, the present Antarctic diversity, will adapt to these changes. Also, we will have the loss of unique endemic diversity because the connectivity between these local populations will be lost, and we will face the phase of genetic diversity in the terrestrial populations. And also predict that there will be a non-native species invasion in terrestrial ecosystems, and the factors of the environment will be changing, and maybe they will be more favorable for non-native species than for the local ones. As one of the examples of the impact of climate change on terrestrial diversity, you can see there are two flowering plant species here. This is the Shamsia antarctica, and this is the zoomed image of the Calabanthus vitensis, another flowering plant. And the scientists predict that their population will increase and they will cover more area in Antarctica now. And actually, there is also some data that supports this. At the same time, we will have the increase in number of the penguin nests. This is the data of the National Antarctic Center. The blue ones are from our island, where our station is located, from Galindus Island. And the green ones is from Cape Tuxen, which is close to our station. This is the part of the continent. And you see that starting from 2011 to 2020, the number of the nest, of penguin nest, is increasing. And this is a very nice image of Gentoo penguin taken in our station. And we might think that, wow, this is cool because the number of penguins increases and the diversity increases. But in fact, this poses a challenge to the local plants in our area. This is a study of the National Antarctic Center. It should be validated, but we are pretty sure in the results already. So here on the top, you have the NDVI index. basically showing the vegetation from 2019 to 2021. And you see that the vegetation decreases. There are less green areas and more black areas. And also here in below, this is the same area. Here you see the moss banks. The moss banks are really important in Antarctica. They are really old, they're really ancient, and they act as carbon sinks in this environment. But when the penguins enter this territory, they supply more nutrients with their feces, and it impacts negatively the local vegetation. So you just see on these pictures how this moss bank is gradually dying from this excess of nutrients provided by penguins. So this is one of the examples of the climate change impact on terrestrial biodiversity that we are observing and studying on our station. Moving to the marine diversity, marine ecosystems in Antarctica are one of the most isolated on Earth, and they're basically isolated by this Antarctic current that is going around Antarctica and separates the water masses of the Southern Ocean from the other oceans. These marine ecosystems are more diverse, much more diverse than terrestrial ones. For instance, there are more than 8,000 benthic species described. You can see them on this beautiful picture from British Antarctic Survey. And this diversity is thought to be second after the coral reefs. At the same time, it really depends also on local stress factors. For instance, this diversity is adapted to ice cover variation, to light variation throughout the seasons. But the temperatures in this environment are relatively stable. This is the picture just for those of you who never been there to know how this system looks in Antarctica near our station. So as with the terrestrial ecosystems, we have positive and negative impacts. The positive impacts are thought to be the loss of the coastal glaciers that will result in new opened areas for biological productivity. So basically marine diversity will have more light, and there will be more phytoplankton blooming there. And this blooming phytoplankton, this microalgae, are thought to be a very prospective carbon sink that will actually might slow the global warming. And on these two pictures, you see the chlorophyll A estimations that is estimated currently. So this is Antarctic Peninsula again, and there are red areas here representing the blooming phytoplankton. And this is what is expected to be in the next decades. So you can see here that in these red areas, they represent the increase in chlorophyll in Antarctic Peninsula and also in some other shelf areas near Antarctica. Moving to the negative impacts. Actually, for marine biodiversity, the negative impacts are much more critical than for the terrestrial biodiversity. First of all, we expect to have reduced krill numbers and altered distribution with a decrease in the sea ice. Actually, this picture illustrates the drop down in krill population from 1980 to 2000, which is estimated being around 80%. This is this krill species that is really important in Antarctica because the whole food web, the marine food web, depends on this. Even the fish and whales and the stability of the whole system depends on this tiny creature. This is the main food resource for all other species in marine ecosystems in Antarctica. Also, one of the negative impacts is that the climate change in the Southern Ocean will influence penguins, albatrosses, seals, and whales, basically through this reduction of krill population. Also, the increased movement of icebergs will destroy local benthic communities. Other consequences include ocean acidification and also the general freshening of seawater, because we'll have more melting, more fresh water entering marine ecosystems, and this will also lead to mass mortality events in krill and also will damage the diverse benthic ecosystems in Antarctica. So the issue that is faced by the marine species is how to adapt to all these awful consequences. And it depends on what species we're talking about. For instance, small creatures with short generation times, like phytoplankton that you can see here. This is the microscopic images of phytoplankton from Antarctica. They can basically evolve because they have small generations. They can just have some mutations and changes in their genetics, and they will evolve to follow these new conditions, to adapt to them. At the same time, bigger creatures, they have a longer generation time, and they might not have time to change their genetics in order to adapt to the current situation. Therefore, they will need to have the so-called phenotypic plasticity. And phenotypic plasticity means having the huge selection of different characteristics, different trends that may help them to adapt to different conditions. But unfortunately, even having all these possibilities to adapt, the scientists, the researchers expect that Antarctic marine species will be poor or very poor at surviving at environmental warming in Antarctica. So this is something that certainly should be studied, followed, and at least we should pay attention to these processes, and we should invest in studying both changes in terrestrial and marine diversity in Antarctica under the climate change. This is just the picture illustrating everything that was said already. So we have the negative consequences of warming in Antarctica. We have the ice melt, basically, that influences different areas in Antarctica. We have increased likelihood of non-native species invasion. Also, we will have increased productivity of phytoplankton because we will have less ice and more light for phytoplankton. Also the krill and some other ice-dependent creatures will for sure change their populations, and it will influence the other species dependent on them, like penguins and whales. And thank you for attention. Sorry, maybe it was a bit too long because it's just a very interesting topic.
Yeah, thank you, Maria. Actually, it's a really interesting topic because, yes, of course, everybody who knows about Antarctica will see and will want to see actually this species, and it's indeed very interesting and cute one. Now we actually go from, I believe you are in Kiev, but now we will go, I hope, to Antarctica. So do we have Oksana? I hope she's online. Yeah, great. Hi, Oksana, how are you?
I'm good. Thank you.
Wow, great. So it's much easier now to talk to Antarctica than here in Egypt sometimes with connection, if be honest. So please share your screen, and Oksana will be talking on what is just behind her, the instrument, I believe, and she will explain more on ozone hole.
Do you see my presentation?
Yes.
Everything is fine.
Yes, okay. Greetings, everybody. My name is Oksana Ivaniha, and today I would like to talk about ozone hole and why it is important. Currently, I am working as ozone observer at Ukrainian Antarctic Station Academic Vernadsky, which in the past was British Faraday Station. Our station exists since the 1950s, so the data collected here is crucially valuable for scientific purposes. Now I am leading this conversation from the station using the data from which and another British station, Haley, in 1984, the ozone hole was discovered. So what is ozone? It is just a small molecule, thanks to which the life on the Earth was able to develop successfully. Naturally, ozone forms from O and O2 with impact of UV radiation and destruct into O and O2 with impact of UV radiation. Naturally, ozone forms a layer in the stratosphere from 15 to 35 kilometers. It acts like a shield, protecting us from the dangerous UV radiation. We have most part of the ozone in the stratosphere, but we have ozone in the troposphere as well. But here, ozone acts like smoke and dangerous, harmful gas. So stratospheric ozone is considered like good ozone, and tropospheric ozone is considered like bad ozone. If UV is not absorbed, high energy UV radiation would reach Earth's surface in amounts that are harmful for a variety of life forms. In humans, increased exposure of UVB radiation raises the risk of skin cancer, cataracts, and suppressing the immune system. We are here now live in the ozone hole conditions, so we can't go outside without sunscreen or sunglasses, because we will have all these illnesses if we will not be careful enough. For ozone monitoring, we are using ground-based instruments like Dobson spectrophotometer, which you can see above me, and ozone balloons, which can measure also vertical profile of ozone, and the remote satellite instrument, which can get global ozone around the globe. With the beginning of the satellite era, we have received instruments which allow us to obtain global ozone distribution. So now we know that ozone amount varies strongly with latitude over the globe, with the largest values occurring at middle and high latitude during most of the year. 90% of the ozone is located in the stratosphere, and ozone layer is higher in a tropical atmosphere and lower in the polar stratosphere. This distribution is a result of large-scale circulation of air in the stratosphere that slowly transport ozone from the tropic, where ozone production is highest, towards the pole. So in the tropics, we will get less ozone than in higher latitudes, because mostly all ozone is transported to higher latitudes. This natural seasonal cycle can be observed clearly in the northern hemisphere, as shown in the figure. Northern hemisphere is shown above, and southern in down figure. With increasing values in Arctic total ozone during winter, a clear maximum in spring, and decreasing values from summer to autumn. In Antarctica, however, a pronounced minimum in total ozone is observed during spring, where there have to be maximum, but we observe minimum. This minimum is known as ozone hole, which is caused by the widespread chemical depletion of ozone in spring by pollutants known as ozone-depleting substances. The severe depletion of the Antarctic ozone layer, known as ozone hole, occur because of the special meteorological and chemical conditions that exist here and nowhere else on the globe. The very low winter temperature in Antarctic stratosphere caused polar stratospheric cloud to form. In Arctic, we have warmer stratosphere because above Arctic we have ocean, and above Antarctica we have land, and land is always colder than water. So Antarctica will be always colder than Arctica. So here polar stratospheric cloud can form in such amount to create an ozone hole. Special reactions that occur in polar stratospheric cloud, combined with the isolation of polar stratospheric air in the polar vortex, allow ozone depletion substances to produce the ozone hole in Antarctic springtime. The main cause of this dramatic ozone depletion is ozone-depleting substances like chlorine, bromine, halons, and others, mainly coming from industrial activity. Measures taken in time, such as Montreal Protocol and its next amendments, have provided decreasing of ozone depletion substances in the atmosphere. This protocol was one of the most successful protocols that climate scientists was accepted. It really helped to decrease the substances in the atmosphere, and we all hope that this trend will continue. However, we still see ozone hole every year with big year-to-year variability of its size and depth. The mean state of ozone hole is controlled by chemical reaction with ozone depleting substances, but variability of ozone hole is connected also to natural factors such as solar cycle and others. But we finally observed stabilization of ozone layer since 2000, when Monroe Protocol procedure started to show the results. In these figures, we can see the ozone hole area and ozone minimum values inside the ozone hole area. And really, after 2000, the values of ozone hole stopped to increasing. And the ozone hole stabilizes its size and slowly starts to decrease its size. On the left figure, we can see the data from the Faraday station. We here have a very long data set, and this data also see that ozone depletion was observed before 2000, and then we see recovering of ozone layer. If we continue to maintain Monroe Protocol procedure, we may expect ozone layer recovering by the end of this century. Hence, the process of recovering takes much more time, the depletion process, because the appearing of ozone hole change atmospheric dynamics. So the process of recovering will be very slow. And my work as ozone scientist here in Antarctica is to monitor this process in order to provide fast reaction to any unexpected changes. Thank you very much for attention.
Thank you, Oksana. It was really very interesting to know about all this, what happened with ozone hole. And I believe that everyone now understands the difference between Arctic and Antarctic. At least, and why it's formed in different these places. But actually, if it's possible, yeah, maybe to show something. So just maybe to show what is behind you. So this is famous instrument.
Yes, I think that we can. This is Dobson spectrophotometer, in which I measure ozone layer. Here is not the same spectrophotometer that on which the ozone hole was discovered, but the same one. And now I maybe can see what we have here outside. Yes. You see our penguins and the snow. Do you see something? Oh,
yeah.
Here, our penguins, which live near us, near our door.
Well, amazing.
And a lot of snow, more than 3 meters of snow. Aerology station, blue buildings. We have a lot of penguins. 20 years ago, there was no penguins, but now more than 3,000 live around our station.
Yeah, we see it's cloudy and supposed to be cold. Here in Egypt, it's especially helpful to see, actually. And yeah, it's nice to know that, yeah, penguins is just marching. So, and they waving to all here in COP and just asking to save them. At least in this cold continent. So, well, thank you, Oksana, so much. Actually, it's really very interesting to see, especially from your window, and to know that ozone hole will be, you know, recover. We very hope, and this is one of positive messages here in Climate Science Summit, where we can say that probably, very probably, if we will mitigate climate change, we will recover with our climate system as well. But it's not what only we have where we can make our Antarctic science, these stations and very well equipped. Actually, this is the best equipped meteorological station of Ukraine, and it is in Antarctica. And today morning we had another session where we were explaining about difficulties of our meteorological network destroyed in this Russian war against Ukraine. And actually we had a high-level representative of WMO who assured us that they will help us to recover in meteorological our network. So we had this very positive message, and I'm really happy to say about this to all our panelists and to all who will listen and who listen online. So we will move now to Olena Marushevska, who will present our another possibility for climate and not only climate study. Olena?
I don't know if you can see me, but even if you can see me, it's just I'm there. Greetings to all the participants. We have a shortcut of electricity in Kiev. So, but I'm with you. I have electricity. I have candles. I don't know if you can see me, but hopefully Svetlana can help to show my presentation. First of all, greetings to all the participants. Svetlana, you are doing such a great job to show and to moderate all of these complicated issues. Thank you very much for this. Unfortunately, today is no electricity in Kiev in my region, so I will just hope you can hear me, at least if you cannot see me. What I want to tell you today is about our great research vessel. This research vessel called former James Clark Ross. I don't know, is it possible to show my presentation? If not, I will. Okay, perfect. Actually, everybody who saw the ship, this vessel, actually British always called it she. It's not he, it's she, it's woman. It's really beautiful, and it's really scientifically well equipped for polar studies. And what today I want to say, I want to present its capacities, and maybe there will be some interest to help to do us joint researches, because you know that Ukraine now is in difficult position, but we don't ask for aid. We ask for additional projects, for joint projects, which could help us. I don't know, can you hear me? Hopefully. And then, so that we could cooperate and we could see. Is it possible? Okay. Can you hear me? I don't know.
Yes, here in Zoom we hear
everything is
you.
fine. Just say when
okay, that's good. I cannot switch on my presentation. Is it? I don't know. Is it? Should I show my screen? Maybe. Let's see. Okay, the demonstration is shown, the right of demonstration as with Svetlana. Svetlana, can you open my presentation, please?
Yeah, now it's projected here, and this is the slide where it's that noosphere is former legendary James Clark Ross.
Okay, because I cannot see it. Maybe it's just some delay. Okay, so if you can turn it down, because I cannot see, maybe there is some delays in the. So what I want to say. First of all, we are very proud that we have such kind of great vessel. It is the vessel was called James Clark Ross. It was owned by British Antarctic Survey, and we know that they really love this vessel. The vessel, it was built in 1990s, and it was one of the flagship vessels of British Antarctic Survey, and it was contributing to many significant researches in Antarctica as well as in Arctica. I really cannot see how to transfer to the next slide, but hopefully you can see it, because I cannot. What I want to say is about the capacities of the ship for all the people. The capacities is really great, that we have up to 46 scientists which could be on board, which makes it possible for complex studies, not only climatic studies, but you know that how climate also affect on biology and chemistry and other surveys. So this the vessel is really good for this. The vessel also has dynamic positioning that it can stay in the same point despite of the waves, ice, and etc. So it can stay at the same point, which makes it good for good monitoring. Also, the good thing that it can travel and be without additional supplies for almost 2 months, actually for 57 days, which is also good, because it means that you can almost travel around the whole Antarctica to see it, visit, so what we say, the vessel is also having different kind of winches, which allows to take samples up to 6 kilometers. So it's quite a well-equipped vessel. So, and what we hope to reach is we're really looking for some kind of collaboration and opportunities to work together with other research teams. We are very happy with that climatologists have already our climatologists so many joint projects with other teams. So we hope there will be more of this kind of projects which will involve our vessel as well into this research. Not sure if you can see escape. But we are very welcome all the initiatives, and there on the presentation there are my contact details, and if there is somebody and some research teams who are interested in cooperation with us and traveling and making climatic and other research using our vessels, we would be really happy to answer and to contribute. So thank you very much. I hope some of my presentation was possible to see.
Thank you, Elena. Actually, it's our reality now in Kiev with these blackouts, power cuts. But you presented very clear. Actually, I'm really happy we're all happy to have this vessel in our Antarctic Center and be able to use it in future. But of course we need more cooperation because this vessel it's pretty expensive to operate. Yes. That's why actually we are we are calling for cooperation and just to say that it's a really very, very good scientific vessel. I've been on this vessel 25 years ago, to be honest, and I was impressed. And it is I've been just a year ago, and I was impressed again in how good condition it is. And we will listen more about this vessel with other presentations of our speakers.
Thank you very much.
I want actually to show you a few things I wanted to show you before, but I didn't say about this. Actually, I have here a few things with me. These things are T-shirt with the emblem of 27th expedition. So virtually they all with us, I hope. They have good connections, so they can be with us and listen for this presentation. And here we have very valuable things, actually, which are, well, postcards with penguins. I don't know if somebody can see this, but it's postcards with stamps from station, with actually on 25th anniversary of our Ukrainian Antarctic station. So I just want to say that we can provide this for those who will make, some interesting questions for us. Maybe not today we can answer them, but in the future, please put these questions under the video, and we will try to reach you. And our panelists, they will judge and say whom will go this nice. And we have here some other stuff actually, which is magnets with different things. So with with this, I guess we will go for our project, which was stopped actually very recently. I mean this project of year of polar prediction. And this time it was a project for winter season, and Ukrainian Antarctic Station participated very, very actively. So we were happy and we were lucky to have equipment for this. So we made launching of radio zones. Do we have David Bromwich? I just don't see all panelists, I believe. David, are you here? Well, I don't think so. No. Okay, so we have Anastasia Chigareva, who actually was one of those young scientists which we need, not need, but we want actually to thank, and yeah, to say much more thanks that we launched actually this program and this year of polar prediction. So Anastasia, are you ready?
Yes, of course. I maybe would a little bit extend my talk because David seems like some technical details and problems as usual. There was like part about what was going on in Antarctica this year, and I just will talk in a few words that this year we polar atmospheric science community organized a great project that was aimed to improve our understanding of weather, atmosphere of Antarctica, and improve our polar forecasting. Actually, so how did we do this? Each Antarctic survey of countries that are presented in Antarctica was contributed by their observations and contributed by their additional observations, mainly radiosonding. So we organized and agreed on some very interesting and challenging atmospheric events. There, like in which understanding of which we are all very interested, and the understanding of this extreme atmospheric events will help us understand polar atmosphere better. So what I'm talking about mainly.
Sorry, Anastasia, I'm sorry to interrupt you. Maybe we can, maybe you can explain this David's actually presentation, because actually it's very good. It's very good. Maybe
sure.
This is general explanation. So we will start this presentation from us. We have this presentation.
Yes, but the only point that your screen, as I noticed, not sharing in Zoom. So yeah, we see just one folder, so it's not actual presentation seen in Zoom. So can you manage this? Because it is just
I'm sorry.
yeah.
See?
Let's say share screen in Zoom. Yeah. I see that you have in your window translation in your room.
And what about other listeners? Because it's actually we translate now.
Yeah, the same. We see only files, only directory with files, not the presentation.
So technical issues is.
Sorry about this. As I
yeah,
said.
that's why Olena can't comment her presentation. It also was the same problem.
Okay, now.
Yes, now it's okay.
It's full screen?
Yes.
Yes, yes.
Okay, so Anastasia,
Okay,
you can-
yeah, perfect. So, so main idea is that it was absolutely free input and contribution and organization. So it was great collaboration of all Antarctic scientists that working in stations, what's working there. So let's start it. Year of polar prediction in Southern Hemisphere actually is some additional and some continue of the project that started at 2013, Polar Prediction Project. At the beginning, it was held in Arctic, and this year it was moved to understanding winter in Antarctic. Previously, it was also for understanding summer meteorological events in Antarctica. So the next slide, please. Okay, and here you can see all the countries and stations that contribute with additional and routine observations to this project. And with the green is highlighted Vernadsky station on Antarctic Peninsula. So you can see that it is great international cooperation, and it is, yeah, just amazing. So we have a mix of routine observations that is made for like everyday observations on each station, and for special observing periods that was previously agreed, we are making extra observations. So next slide, please. Just radio zonding is give us not much information, mainly for understanding supercooled liquid water in atmosphere that can describe clouds' existence and presence and how it is extent. We use extra special sensors that is called atmosphere zone sensors that helped a lot, and it was launched on these highlighted stations. So next slide, please. Okay, again, that I was talk previously, two main reason to make this project is to understand what's going on in atmosphere, and with these instruments understand what's going on in polar climate system and ecosystem, how it is impact on changing of ecosystems that we was listening previously. So next slide, please. Okay, yeah, I'm not sure that I can comment this slide. Yeah, reducing of sea ice. So yeah, so maybe next slide, please. So this is how it looks like a typical forecast for extreme precipitation events, and with this yellow and red highlighted regions represented mainly regions with very high presence of moisture in atmosphere that could be transferred to intense precipitation, and typically this is how it looks like this very, let's say, moisture region around Antarctica. So we can see that mainly Antarctica is kind of dry territory. However, this intense moisture intrusions from lower latitudes impact very extremely borders of Antarctica and borders of Antarctic ecosystem. So next slide, please. And during all winter period that was held from May to August, there was in general 7 target observing periods that was in general about 1 week duration, and for Antarctic Peninsula, it was just 5 of them. So yeah, and on the slides you can see particularly our guys from Vernadsky station, and more about this I will talk later. So next slide, please. So mainly target observing periods was characterized with very intense precipitation, very intense winds, and it was very challenging to actually make any kind of observation during this time. However, it is that is why it is so interesting. So next slide, please. Yeah, some summary of this project you can see on the slide. However, the main summary is that great teamwork of Antarctic community is kind of unbelievable scale, and we are very happy that Vernadsky take part in this teamwork, and thanks to this teamwork, now we have a possibility to have extended data that will help us understand what's going on in Antarctica as in a less research region. Still, it is like a big white spot on our map of science. So this part, I think, is finished. And I would
thank you so much. Actually, yeah, Nastya, you presented very well this part, and now will be another part, and I will just say maybe a few words about you, because Anastasia is my PhD student, and I'm really proud of her because. Yeah, she made this project possible actually at Vernadsky station, and she launched this first radio zone, and then Anastasia, you can continue.
Yeah, so may I share the screen, or you?
We project actually. So with first slide, if you can say this.
Okay. Something again happened, and I could not see presentation in Zoom. Sorry. Yeah. Okay, great, perfect. So yeah, thank you, Svetlana, for introduction. And yeah, I just would like to highlight that it is a spectacular year for Ukrainian atmospheric polar science, because we launched these radio zones for the first time during last 30 years, and it is a great step in Ukrainian meteorological science. So yeah, last radio zones were launching maybe like 5 years before British Antarctic Survey transfer Vernadsky station to Ukraine. So at the moment, during this year, we were provided just radio zonding for special observing periods, not routinely, but in future we are going to make this observation routinely and round the year for Vernadsky and seasonal for from the Noosphere research vessel. So next slide, please. Yeah, and great work have been done to make this real, and it was like few teams of scientists working on it. I participated in seasonal teams that was working on installation, first test runs, some methodology implementation, and yeah, as you can see on the right picture, sometimes it's not enough to be just one person who launching the radio zone. You have to be like few people keeping each other, because it could be very tricky around these extreme events. And next slide, please. So main work for this contribution to a year of polar prediction have been done by wintering team that is now still on Vernadsky station, and sometimes it is we was not able to launch radiozones because wind speeds and precipitation was too much intense, so it was even not safety for health. Sometimes equipment don't want to work in these conditions. However, we succeed with most part of radiozonding in this project. So next slide, please. Oh, okay, so sorry, it seems like not, yeah. I just wanted to say that in general, radiozones provide us vertical information about vertical structure of atmosphere up to 20 kilometer, and yeah, it is very broad and interesting information, and we will supplement this with routine observations from Vernadsky, and now we proceed the data and expect in the near future that this data will improve our forecasting, and we'll see how it will improve our understanding of polar atmosphere and Antarctic atmosphere. Thank you very much for your attention, and I'm very happy to answer any of your questions about this project and how it's going on Vernadsky station. Thank you.
Thank you, Anastasia. Actually, yeah, it was interesting work, and we have a lot of data now, and we will do our research of this interesting events of extreme precipitation. And it's actually remind me how we collect this precipitation at the station and made these samples, these special samples for International Atomic Agency. And I'm really happy to introduce for you Yulia Vystovna. Please come. It's our just one speaker who is here. Okay, I can give you another, I guess, mic. Yeah. So and you need to. Yes, and you will explain us why we took this sample actually station, and many meteorologists here we have who actually made this for years. So please.
Thank you very much. In my presentation I sent you, you have
Yeah,
PowerPoint.
yes, yeah.
Please start, because I prepared several slides. Before I will talk, I will start what is actually isotope hydrology means and what International Atomic Energy Agency doing in Antarctica. This is probably the question what people ask. If you look about isotopes, I was born in Kharkiv. Whenever I move from one country to another country, I'm moving because I'm born in Kharkiv. So anyway, I stay as person what I was born in Kharkiv. This is the same with isotopes and water molecule. Water molecule been born under the ocean, and we know it was born under this ocean, under this location. Whenever this water moves through the hydrological cycle, we can trace it. The same with age. I know my age, and water has age, and isotopes help us understand what age of water and why it's important to know age of water. Water can have from months, from days to 1,000 years old. And for example, I will give you some example on groundwater. It's not related to Antarctica, but to understanding. If we are using groundwater, was born, what they have age 3 years, we need 3 years to replenish this aquifer. If groundwater, what we are using 1,000 years, or this groundwater been drink by dinosaurs, it needs 1,000 years to replenish this aquifer. This is isotope hydrology work on. We also work in Antarctica, and we have very strong connection to Antarctica because this is the longest records of isotope precipitation. Please let me to describe this magic of isotope hydrology in Antarctica. Next slide. So what we are studying with isotopes and precipitation, we can answer, as I explained you, where did the water come from? Is it from local sources, or is it from Mediterranean Sea, or is it from ocean? How water moved to this location? It was by atmospheric oscillation, by different atmospheric pressure. How long water stay on the earth? How old is your rivers? Also, we answer the question, how how much water available, how you can continue to use your water. This is important to know. We are thinking about water is a renewable source. Yes, it's renewable, but you need 1,000 years to renew your water. Next slide, please. Only one slide with formula. This is to describe, we are working with two types of isotopes. We are looking inside of water molecule. And we are using stable isotopes and radioactive isotopes. Stable isotopes, they are not decay in time. It's like water, deuterium, oxygen 18. This is what we are monitoring in Antarctica. But also we have radioactive isotopes. They decay in time. And by decay in time, we are tracing the age. Next slide, please. How it's related to hydrometeorological measurements. Isotopes very connect to temperature. If temperature grows, it's more evaporation. For example, I have my water, and you probably know if you open water, it will start evaporating. And you heard about heavy water. I think everyone heard what's mean heavy water. Heavy water, it's mean what light isotopes left your water. That is why this is one of the description of the simple isotope hydrology. Why we are talking about heavy water? Now you know, because it's light isotopes, they went with evaporation. And this is we are using to understand the hydrological cycle and the application. It's helped us also to differentiate the trajectory of the air masses. It's important to know because air masses are changing with the cycle and under the different pressure. Some air masses bring in floods, very flash floods or heavy floods, and some air in absence of rain, it's mean drought condition, what is also controlled by atmospheric oscillation. This is what we are using isotopes. And here I presented some of the example of isotopes in Vienna. You can see its temperature is growing and isotope is growing. Isotope integrate much more parameters. You can see in time we observe the decrease. Next slide, please. So Antarctica in one of the many stations. We have a global network of isotopes and precipitation. You can see here the map with the station, what active stations in green. We are developing some stations, and we have also some network what is not reporting to us. How people using birth isotopes, people even using to understand migration of birds. And if you, for example, if you moved from southern hemisphere to northern hemisphere, in your blood, we will trace it because you consume water and food from different locations during your movement. Isotopes cannot lie. Isotopes also can answer, are you really vegetarian or not? Here, unfortunately, we cannot answer with stable water isotopes in Antarctica, but generally isotopes, they're really fingerprinted of the memory what we did. The same with stable isotopes and water molecule. So Antarctica in one of the station, and we have 3 stations, but Vernadsky, we have the longest records without any gaps. Next slide, please. And how we are working, how we are operating our global network of isotopes in precipitation. We have a station what we show. After some member states, some our counterparts, they analyzing by their self and send us data, or they send us samples like in Antarctica, precipitation accumulated during 1 month and ship us the samples, and we analyzing using, just prepared some slides to look at very scientific. We analyzing on laser spectrometry in our laboratory in Vienna. So Antarctica samples come to us in Vienna, analyzed and put in the database. Next slide, please. Some history, probably it's quite short history. Vernadsky station, it was starting from 64. We have the first isotope data, but before it was a station of Faraday from United Kingdoms. We also have Halley Bay station, a little bit 1 year later. That is why Vernadsky is oldest one year earlier. We have also Rotera Point. Oh, like we have like 30, almost 30 years of the data. So the next one. If you look at this graph, so we have Vernadsky just marked in here. Isotopes is growing, precipitation temperature is growing in Vernadsky. What is good? But we have no any gaps actually, if we do modeling, we can trace how air masses was changing during these long-term periods. And in Vernadsky, for example, in Hong Kong, we have some data. So I just put some comparison with other stations, what we have in long term to see how isotopes. You can see Addis Ababa, we have some change, shift in isotopes. It means it's oscillation been changed. In Cape Town, temperature growing very fast and evaporation very enhanced. In Hong Kong, it's impacted by monsoon. So we are tracing different type of atmospheric processes using stable isotopes. Next slide, please. So why we actually need it for broader audience? The first, we are validating global climate models because we would like to know what will happen in future. This is question what we are coming from our human nature. We would like to know what will happen, and this is isotopes to help us to validate with climate models, especially oscillation. Melting cryosphere, this is sad subject, but after when I saw presentation on ozone, I have some optimism, but if we act, we can make change. But cryosphere melting, it's disclosed information and data on past climate, what was in the past, because it was difficult to make this analysis. So opening of the melting conditions help us understand biological and hydrological processes of the past, and we are using isotopes engaged for that. Also, we are understanding the melting of cryosphere on hydrological side because melted water, it's always very depleted one. So it's very different from the water from atmospheric sources. And we are using it also in analytical. So Antarctica is one of the analytical standard in our measurements and our analytical processes. But also in data interpretation, this is some small photo we are doing in alpine glaciers. It's our expedition in alpine glaciers because alpine glaciers is also melting. So we are taking samples to understand the age of these glaciers. So thank you very much. Thank you very much for this invitation to participate in this session. It was really a pleasure to be connected virtually to Antarctica. Thank you.
No, thank you so much. Actually, now we understand much better what we were doing, what I was doing there, and why, actually, and for what. And now I understand how much it's really important for climate study in first hand, actually. So thank you so much.
Thank you so much.
Stay with us, please. And I hope we will have questions, and then we can pass it to you. Okay, so with our speakers, actually, with this introduction to this much more global view on precipitation and processes, I guess we now will go to this our other project, which is about polar res. So I see Priscilla is already here and ready to go, I hope. And she will explain, and it's another project where Antarctic Center is involved. We just started recently, just 1 year, and unfortunately, this almost all year, unfortunately, was a very difficult time for us. But anyway, I want Priscilla, yeah, please, the floor is yours. We cannot hear you, sorry.
Hello, greetings. Can you hear me?
Yes, now yes.
Okay. Let me see if I can go back. Hang on.
I guess, sorry, I guess, yeah, everything is fine?
Yeah.
Yeah, good.
Okay. So thank you very much for the opportunity to participate and present some information about polar res. So our project, just an overview for everyone, it's funded by the European Union's Horizon 2020 Research and Innovation Programme. It's a large international project with a budget of almost 8 million euros. And it started, as Svetlana said rightly, 1 year ago, and it's a 4-year project. There are 17 partners or institutions involved in the project from 9 European countries. And we are very happy to have 2 Ukrainian institutions part of our project. Their logos are shown here, the National Antarctic Scientific Center of Ukraine and the Institute of Mathematics, Machines and Systems Problems of Ukraine. And the project is coordinated by me in Norse, which is here in Bergen, Norway. Our goal is to provide more reliable and more confident climate information for assessing impacts in the Arctic and Antarctic. And we heard some very nice presentations earlier from Ukrainian scientists about some of the ecosystems in Antarctica. And so these are things we are interested in supporting and assessing a little bit more. And so the question is, how will we achieve this? And there are really two approaches to this. And the first of these is to close some of the knowledge gaps, and there are many, in the polar climate system, and a better understanding of its role in the global climate. So the polar climate is exerts an influence on the global climate, which makes it very important for many reasons and for everybody. But it is also influenced by the global climate. And the second approach is to apply a storylines approach, a new approach to addressing uncertainty and to better communicate uncertainty in climate information. So in the project, we take what we call a holistic or a collective view of the entire climate system of the polar regions. And that's kind of encompassed here in this image. So we can see that we have global climate features like the AMOC, the Atlantic Meridional Overturning Circulation, which can transport heat into the polar regions and heat out of towards the tropics. And here on the right, we have an image of different processes that are happening in the Arctic and processes in the Antarctic. And there are lots of similarities between both the Arctic and Arctic in terms of cloud aerosol interactions, for example. And so we build on the synergies of the two polar regions to develop a better understanding of these processes and how they shape the polar climates. I won't say a lot about these because I think Dennis will say a little bit more about those in his slides and highlight some of the really important work that they are doing in our project. But I'll just say a little bit about the storylines approach and how we are developing climate information, or at least the concept that we are using to develop this information in our project. So the first step is to look at how the global climate is shaping the polar climate. So we are looking at this CMIP6 data, which is very much a strong feature of the IPCC reports, and to identify different circulation patterns in the global climate that influence the Arctic and those that influence the Antarctic. And so an example is shown here where we look at the Arctic amplification and how different GCMs project changes in Arctic amplification. Then we will use regional climate models to downscale this global information to very high resolutions, where they'll be more useful for impact assessments in the Arctic and the Antarctic. And then we will use this information to assess a variety of impacts, including marine ecosystems, Arctic wildfires, the dispersal of radionuclide particles in the Arctic, as well as permafrost thaw. And so without further ado, I'll just say thank you very much for your time, and I'll hand you over to Dennis, who will give you much greater information and detail about what they are doing in this project. So thank you very much.
Thank you, Priscilla. Actually, yeah, it's very clear now that we will work in this big team, and we'll try to do our best. And here we have actually extension of the presentation from Denis Vishniak, who is head of Department of Physics of the Atmosphere and Geospace. So Denis, what about you?
Hello. Hello. So now, thank you, Priscilla, for this general information about project. And I only talk a little more about our NANS activity in this project. Yes, so now I try to share my screen, and also I stop my video because I have no stable internet. Oh, just a moment. Where is it? Can you see my screen now?
Yes, we can, but not
Okay.
in,
I try to stop video. Yeah.
yeah.
And full screen. Yes. So where is it? It should be. Oh, it should be here. Sorry. Yeah.
Can you put it in? Okay.
Oh no. I don't know. It didn't work. Maybe this. Oh yeah. So a little bit about NANS in PolarRes. So PolarRes is a quite big project with near 14 worked tasks, and NANS, National Antarctic Scientific Center, according to our project plan, should be involved into 5 tasks from this 14. So it is on the screen is task 3.4, investigate the impact of changes in global circulation on the Antarctic at high resolution. It is cloud microphysics, including aerosol cloud interaction and precipitation. It is aerosol cloud interaction over polynas and extreme precipitation and temperature events over coastal West Antarctica. Also, we involved in dissemination, cooperation with stakeholders, synergy, and policy outreach is a big work package with several tasks also. So I don't told very in detail this, but you can see that in every task, it's our main instruments there is a polar WRF regional atmospheric model. It may be as a main or additional instrument for our analysis. And also, of course, other data which are available in our scope also will be involved, like reanalysis, climate forecast from climate intercomparison project, and observation. This project not closely related to Vernadsky station, but covers an area of our research interest, and also maybe some data from Vernadsky will be directly involved here in the project. Yes, so this is such our planet activity. And just about just little about what is a polar WRF model. It's a regional climate model which work like this. Take some region, and this model can achieve a resolution at near 1 kilometer in our task. So it will be used to investigate local spatial variation in snow accumulation, in temperature and melt association with extreme events, and some other tasks. It's how it works. It's like this: some territory it takes for modeling, and then we obtain different weather parameters filed or check characteristics of these parameters. This is first experiment which was done for this moment, and also we have a comparison with observation data, modeling and observation data. On this graphs, for example, you can see color lines is modeling temperature, and black line is observation temperature. So the correspondence is quite good for modeling. Means that the model is a good instrument for our researchers. So it's just an example. And other words about our grid plans that it should be noted that we have now we have a problem with our office building. It was damaged during this Russian aggression, and also electricity instability, like you showed it already. So this plan is under question, and I'm sure that how it will be done in full. Yes. So it's main notice about all this. But okay, we will hope that everything will be good. So maybe during months we repair our electricity system, and everything will go ahead. So thank you for your attention.
Thank you, Denise. Actually, yeah, I guess we need. Yeah, this is the last slide with this big fire. Of course, it was really big damage for office of National Antarctic Center, and of course we will do our best to continue our work. And here, actually, just to continue, I want to invite Alexander Koloskov, who is now will present from Canada. But as Yulia just explained us with radio tops, I hope and I'm sure he takes his signature from Kharkiv. So the same city, actually. So Alexander, you can do it once again. Yeah.
Okay. Can you hear me?
Yeah, we can hear you. And please,
and
yes.
Do you see my screen?
Yeah, everything is fine. Yes.
We'll see. Okay. Thank you very much. And first of all, I would like to say that it is a pleasure for me to have this opportunity to present our result and this meeting. And of course, it's not possible to tell all the things about the Schumann resonance, but I will try to explain only some main ideas. So on this slide, you can see the lightning. This is the lightning is the common event, but very important. And each lightning produces the strong electromagnetic pulse. And this electromagnetic pulse can propagate depending on the waveband to the different distance. But for some reason, do you hear me?
Yes.
It's fine.
Yes, for some reason, I cannot change the slide. What? Mm-hmm. Okay.
I don't know.
Okay. Oops. Page down.
You need to solve it by yourself.
Okay. I will. Strange.
I see you have a pen. I don't know why.
Okay, I will. Oh, okay. Yeah. Without pen, it will be much better, I think. Okay. So now you can see these very long waves from lightning, which can propagate around on the globe. Here you can see some model waves. But also it's possible to measure these waves on every place on the Earth, in principle. And each lightning produce such waves, and these waves propagate around the Earth, and it's possible to see a signature from all lightning all over the world in a single place. And the Ukrainian Antarctic Station is very good place to do this, because if you can see the typical spectra of the ELF waves that we have in Antarctica, we can clearly see these signatures of Schumann resonance. This is several peaks starting at 8 Hertz, and 14 gigahertz, 20 gigahertz, and so on, up to 6 or even 7 maximums. And the information about lightning is contained in the behavior of these signals. Here you can see the typical spectrogram from 2 channels of magnetometer that we have in Antarctica. You can see the changes of intensity, and if you make more precise look, you will also see the changes of frequency. And using and studying these changes is possible using the some model prediction to calculate, to estimate the behavior of lightning all over the planet. It's possible, of course, to see it from the space, but from the space you can see only small amount of the area of sea surface, but from the ground observation and possible to see all lightning. The main lightning is situated in the tropical belt in Asia, Africa, America, and approximately 85% of lightning situated there. And as you see before, in Antarctica, we can see very clear picture of this lightning. Because several things. First of all, there is no local lightning at all, and we have very good signal to noise condition in Antarctica. And secondly, there is no industrial noise also. So these two factors give possibility to make observation of lightning very precisely. That's why we start this observation in Antarctica in 2002. And since that time, we have uninterrupted arrays of Schumann resonance signals. And for the moment, it's the longest array of such type acceptable in Antarctica for the best of my knowledge. In 2013, we started the same observation in Arctica, in Svalbard. So now we have a long array from 2 points, from 2 polar points. I can use it to estimate some climatic effects. This is the photos of our the layout of our observation points in academic Vernadsky and at Svalbard. And I will show you only small examples of this observation. This is changes of intensities of Schumann resonance signals in 2002 to 2020, observed in Antarctica. And one can see this big trend. If I will have time, I will show you this, explain this trend. But also one can see these changes of intensity from year to year. The blue curve corresponds to Antarctic, and the red curve correspond to Arctic. And why we see these trends? One can say that the lightning situated in the tropical belt, there are no big changes of intensity in the tropical belt. And why we see these seasonal changes? But we can see these seasonal changes because the lightning in move on above sun point. Here you can see the animation, and you can see that the above sun point change location. And the lightning in moves along the continent from the southern hemisphere to the northern hemisphere through the season. And the area of land is different on these two hemispheres. That's why the number of lightning and intensity of lightning is changed, and it's possible to use these data to estimate the changes of the number of lightning and intensity of lightning using this data. And our data show that, for example, according to observation from the space, which is very expensive, of course, we can see the changes of 44.3%. According to our observation, the average changes is 44%. So it's very close values, and we can use so simple in principle equipment to investigate and study the lightning all over the world. So we have in our hands good tools for investigation of the changes of light in global scope. And of course, it's possible to use these data to study the changes of the temperature. The formation of thunderstorm clouds is related to the changes of evaporation and depends on the heating of the surface, and it's possible to find the correlation between the number of lightning. This is evolution of thunderstorm days in São Paulo local data, and this is the temperature, and possible to see the correlation between these two curves. But this is local event, and using the Schumann resonance, it's possible to study this in global scale. And this idea was proposed by Earl Williams, who from MIT, who demonstrate some correlation between the Schumann intensity and the temperature. And when try to look how we can use our data obtained in Vernadsky to see these correlations. And here you see our estimations. View the data from NOAA National Center of Environment Information available from this link, and to calculate the surface temperature in this area from about 200 of stations. This area corresponds to the main area covered by lightning in Africa, and also we can select the signal of Schumann resonances from Africa using the polarization technique, and we can compare the mean changes of the temperature in this area with the changes of the intensity of Schumann resonance signals, and then average this data for several years. The same procedure we use for the South America. And now you can see this result. This is intensity, seasonal changes of intensity of Schumann resonance. And this is changes of temperature in Africa, in this region, and in America, in this figure. You can see very good correlation. So this experiment demonstrate that Schumann resonance is very effective tools to study global effects like lightning, and probably it's the indicator of global temperature. But it's if you will return to the previous slide, you can see this very big trend. From 11 years. This is effect of the changes of ionosphere because of this solar cycle. And this trend is much bigger than the changes of temperature that we can study using these tools. So now we have the thermometer, the global thermometer, to measure the temperature, but we need to calibrate this thermometer. We need to continue our measurements and to separate the effect of the medium from the effect of the source. If we will do so, we will use the effective tool to study the global temperature. Thank you for your attention.
Thank you, Alexander. It was really interesting to know how actually, yeah, this lightning can help and can actually really correlate with all other issues with climate change, with rising temperature. And from this lightning, we will go to a bit higher to geospace, and Andrei Zalizovsky will help us to understand about this. Andrei is, as far as I know, from Kharkiv right now. So how are you there?
I'm fine. Yes. We are from Ukraine, from Kharkiv, and we are more lucky. In comparison with our Kyiv colleagues, we have electricity. Do you hear me? Svetlana?
Yes.
Yeah, everything is fine.
Okay. Okay, and I'll tell you about geospace research at Vernadsky station. And first of all, I would like to tell many thanks to Svetlana, to other organizers of this summit. It is an honor for me to make a presentation here. And what is space weather and space climate? It is very similar to the classical weather and space, but it is about the upper atmosphere. So the weather there has many similar features, but not all. So why it is important for us? Because we are living in near Earth space right now, and so we use satellite navigation. Right now we use satellite communication, satellite remote sensing, and so on. So it is very important to all ground satellite systems. And sometimes where the storms in geospace become too severe, it could provide effects on the ground as well. So today blackout in Kyiv caused, unfortunately, not by space weather, but sometimes it could happen. Okay, the differences. The parameters in the space are mostly inaccessible to our senses. So therefore we invent the visual image. And we need more parameters to describe the weather in geospace. Why it happened? Because so the first problem, sun is quickly variable value in ultraviolet X-ray, which ionize the gas, and very variable in the emission of corpuscular emission too. The medium at the geospace consists of natural and ionized components. So they depend on both thermo and electromagnetic processes. And there's something like competition between thermodynamics and electrodynamics there. And the magnetic field and its variations has a strong impact on space weather. So we need much more sensors and observatories for obtaining the raw space weather and space climate data. Right now, we have approximately 100, maybe 150 ionozones, similar value of geomagnetic observatories is about ground-based observation. And the distances between these observatories is much bigger in comparison with correlation radio of space weather phenomena. And moreover, we observed significant anthropogenic impact on the space weather and space climate. And so why it can happen? So the first link is internal atmospheric waves, like atmospheric gravity waves.
Andrei, are you here? It seems that something wrong with connection. Okay, just recognizing that he is in Kharkiv now, and it could be just cut, electricity cut. So, Andrei,
I'm here. Sorry.
there was some problem actually with connection.
Okay.
So,
can you hear me?
yeah, we can, and you can. I guess next slide should be at least.
Okay, right now I'm here. So we observed from Antarctica so significant impact from below on the space weather, both anthropogenic impact and traditional weather and climate impact on the space weather. Why the Antarctic Peninsula is a very convenient place for carry out this observation. This unique place. And at this area, we have very strong cyclone activity. We have a border of geomagnetic anomaly. And due to low inclination, we have a very good condition for energy transfer from natural atmosphere to ionized gas. And due to that, we can see very strong impact of natural atmosphere on geospace conditions. So we see Weddell-Sea ionospheric anomaly. What is that? So the concentration in the ionosphere during the summertime over the Vernadsky station, the midnight is much bigger in comparison with midday, and this inversion observed at the Antarctic Peninsula area only. One more point: we have very serious geospace or space weather observatory at our station, and very important point that the observation, the ionospheric sounding and geomagnetic observation started there in the late 50s of previous year, so previous century. So right now we have more than 60 years of non-stop, almost non-stop, simultaneous geospace observation. So right now we can analyze not the space weather only. We have very valid information about the space climate. So more than 60 years of continuous observation at this place, from Faraday time to Vernadsky. So I would like to show some examples of space climate at this area. So you can see the variation of critical frequency over the Vernadsky station. So right now we use 2 ionozones at the station, and ionozones working there actually since 50s. And this is 2 solar cycles, and we can compare the previous solar cycle. It was more strong with last one, and we see that previous one was more strong, and we have response at our ionosphere. So the electron concentration is much bigger here. So what is that? It is median height time diagrams of the plasma density over the Vernadsky at the different seasons. And here at December, you can see classical inversion. So this local time and at midnight, we have much more ionization in comparison with midday. And it is very possible to analyze the nature of this phenomena. So we compare this effect when we have low and higher solar activity, and we see some morphological features, and this data could be, and actually this data is used to improve, update the ionospheric models right now. And so this is conclusions about the Weddell-Sea anomaly, this climatology of this anomaly. And I will tell more about another observation place. So notice here, this ship, we have had the presentation already about that. And I will tell about the possibility of this ship as a space weather observatory. So during the first voyage of North here to Vernadsky, we used some different antennas here. So two types of HF antenna. First HF antenna used for the receiving side of ion zone that we developed and installed 5 years ago. Install our new Doppler ionizon at Vernadsky station, and this voyage we organize the receiving position, passive position at the noosphere. And I would like to tell you that this unique for today, the receiving side of ionizon on board the ship. So we, during the moving of noosphere, we can measure the parameters of ionosphere at the two areas, and the distance between this area change with moving of the ship. And one more, this mast that use as for the measurements by two Doppler HF receivers. Okay, and this is James Clark Ross in Odessa, in Antarctica, and we carried out these measurements. And it is very important. I told already that we feel very big lack of the geospace observatories, and one more observatory, moving observatory, is very important for our science and our services. And what we was very lucky that the noosphere was near the equator when the war started. That was the position of noosphere 24th of February. And some results. So this is examples of the ionograms which we measured at the Vernadsky station, and using the same signal, this is oblique ionogram on board the noosphere. And this is a similar examples, but first one, this vertical ionogram obtained in Ukraine near Zmiev town, Kharkiv region. And this is oblique ionogram when the ship was near Odessa. And we receive, and now we are analyzing this ionogram by her way from Odessa to the Greece coast. And from Punta Arenas to Vernadsky, we can compare vertical and oblique ionogram obtained over the Antarctic Peninsula and Drake Passage. And one more results on very low frequency band. It is about previous presentation of Alexander Koloskov. This is observation of thunderstorm activity in very low frequency band. And we use this data together with ELF observation in Antarctica and Arctic. Sasha talked about that in previous report. And first of all, we can analyze the position of thunderstorm centers. And one more point, we estimate the parameters of D region of ionosphere using this tweak atmospherics. And we hope and looking forward to continue this observation both on board and on site the station. So thank you very much for your attention, and
Thank you.
I
Thank you.
hope
And
the
we,
space weather and space climate activity will be continued at the Antarctica. I see.
okay, so we see this nice penguins near our flag in Antarctica. We saw it many times. Who were there? I mean, and we have
Yes.
online.
Antenna of ionizon above these penguins.
Okay, yeah, it's near
we
Amazon.
demonstrate our antenna by this slide.
Okay, so at this moment we heard a lot about different science actually, and I want to ask Alexander Bereska Yeah. So we have actually another project with Antarctic Center, and it's about open data. Today we already heard here in this pavilion about open data, so I made this presentation on behalf of Alexander, but now I really pleased to give you floor. So please, Alexander, floor is yours.
Thanks, Svetlana. Can you hear me now?
Yeah.
Okay, so it's a great pleasure for me to be here. My name is Alexander Berescu. I'm associated professor at Lviv Polytechnic National University, manager of Optima project, and also president of Eurodocs, the European Council of Doctoral Candidates and Junior Researchers. And I have a pleasure to collaborate with Svetlana on one project, which is a European Union funded project under the Erasmus Plus program. And let me briefly introduce it. One second. I hope you can see this now. Yes?
Just full screen if...
Yes, it's full screen now.
Not yet.
Unfortunately, I don't think I will be able to do that now, but I hope that you still see it, okay? So as I said, just as a 3-year Erasmus Plus funded project, which is under capacity building in higher education and coordinated by Lviv Polytechnic. I will very briefly describe the consortium. We have many European universities. Can you see my next slide or not?
We can see your PowerPoint with slides. Yeah, but
okay,
no.
let's be like this. So it's better than, yeah, okay. So as I said, we have a consortium of several universities in Europe. And also, we are very much happy to have National Antarctic Scientific Center among our partners. So the main problem we are dealing with is an insufficient quality assurance and low level of internationalization of the Ukrainian higher education system, right? And also lack of recognition of values of academic integrity. And we propose an innovative approach as integrity is based on the fundamental principle of transparency, which is one of the main ethical principles in research and education. And transparency is also celebrated as the most important principle alongside integrity in scientific and educational communities. And transparency is also at the core of open science, which is an more transparent, more open approach to a research process. If you are aware, so Ukraine has recently adopted a national plan for open science. So we hope this will help progress in Ukraine as well. So what we aim to do is to introduce more open and transparent practices leading to increased academic integrity, leading to improved education quality. And we want to do this by introducing open peer review platform to support various academic conferences in Ukraine and develop curricula to introduce special courses on open science in undergraduate and postgraduate curricula in Ukrainian universities. Everything is logical, but you can ask, where is climate action here? Where is climate change here, right? So our initial idea was to explain open science on examples of climate action. And for this reason, we invited National Antarctic Scientific Center to help us to become a partner and to bring this expertise to the project. So to be honest, I was very happy to see that this year, the topic of Open Access Week was actually open for climate justice. So actually we did something first, which was then continued on international and global level. And we actually united, let's say, movement for climate justice and movement for open science, because they have many things in common, and also important aspect of open science, such as open data, can be used and is already widely used in climate action activities and climate science to foster change. Our project has already many results. I will not perhaps focus on them, but I would just like to advertise our social media channels. So if you are interested in how we combine open science and climate action in one project, in curricula and other project activities, you are most welcome to join us on social media and ask any questions. Also, at the moment, we are conducting a national survey in Ukraine. So if you are a Ukrainian researcher, you are most welcome to join our survey for us to give us better understanding of how open science can be implemented in Ukraine. What are the perception of values of academic integrity? And then this will help us not only to bring open science to Ukraine, but also foster climate action with the help of open data and other open resources available. Thank you very much for your attention, and thanks for the opportunity to have this short introduction. If you have any questions regarding this, please feel free to contact me on email or social media. Both me and all the Optima project team are open for collaboration. By the way, Optima stands for Open Practices, Transparency and Integrity for Modern Academia. Thank you, Svetlana.
Thank you, Alexander. Actually, yeah, it's very good to have you here and to speak on this openness actually of not only scientific data, but for climate justice. And actually today morning, I spoke that due to this openness, I guess, we have a much better situation even in this war, because when we open all these records to the world and show to the world our enemy, so we were trusted actually much better. So we open society, we use open, I guess we will continue to do this science in Antarctica as well. With this, I just want maybe to summarize a bit, because today we had, we already heard so nice presentations all over the globe. I believe that we had from Antarctica, of course, we still have online Antarctica here. We had the presentation from Kiev without electricity, and from Kharkiv, and from United States, Anastasia and David already, I guess, with us, and I'm really very sorry that with this mess, with this presentation. Canada, Alexander Koloskov, and I believe Alexander Bereska, you're not in Ukraine, I guess in Prague, you said. So all over the globe, we come together to speak on science and JOS. And I guess our panel is very good, you know, conclusion. Yulia, yeah, the only person here actually is Yulia, who were with me. And it's really a great pleasure to have you here with us all, because you really, it's innovation we can use with all the screens, but much better, of course, to have somebody just near. And I really hope that one day we all will be together. I hope in our renovated Ukrainian Antarctic Center in Kiev, where we will continue our work in Antarctica. And with this, I again want to thank all speakers. And last but not least, actually, not this presentation, I'm sorry, but with 00, I just wanted to thank actually our army to provide us safety and to help us actually to the next one. We want to thank actually all of us, not only Ukrainians, in fact, but all, I guess, people in the world, to our army, to our territorial defense unit, and to all volunteers and all international community who support us. So with this, I ask you, stand with Ukraine to our victory, and this victory will be soon, I'm pretty sure. So with this, слава Україні, героям слава. Thank you.
Now in Antarctica, sun appears and we can see sun halo between the clouds. So this is a sign that the sun in our future is near and the victory is close.
Beside the Galo and Sun, we see the mast of ionizant antenna there.
Yeah.
Yes.
The
And I need to
weather
say
change-
that now we have 3 ionozones at our station, one near the station, a distant one. So we have possibility to study all the things here in these devices.
Okay, thank you very much, Svetlana. Thank you very much all. It was very interesting.